The topic for today is basically maximum flow, but specifically I want to talk about the Edmonds-Karp algorithm and the Hopcroft-Karp algorithm for bipartite matching.
Are we supposed to see? I don't see the paper.
I'm sorry, you don't see the paper, right? That's actually because I haven't started sharing. My apologies. All right, let me. Okay, do you see it now?
Yes, thank you.
All right. Somewhat annoyingly, there is this. Somehow Zoom is popping up in the wrong place. So we're going to talk about the Edmonds-Karp algorithm and Hopcroft-Karp for bipartite matching. So let me just recall what max flow is. So we're given a directed graph, a digraph G, with a designated source vertex S and a destination T. So these are two vertices, S and T, and integer capacities CE on every, instead of edge, I'm going to say arc. And the reason I say arc is I mean a directed edge. And the reason for this is that between two vertices, you may have two arcs, and you can have different capacities on these. So you can have CUV, that's the forward capacity, and you may have a different capacity, CVU, which may not be equal. And so the idea is you have some kind of graph. You have S and T. So one of the ways this is thought about is maybe you're a company that needs to send trucks full of goods from some source to a destination, and each edge or arc has a capacity. There's only so many trucks you can send on a particular road. And those capacities may be different because maybe the capacity here is 0 because it's a one-way street, and here is 10. So you can have capacities, this is not symmetric. And so you have capacities given all over your network or your graph, and you need to route as much flow as possible. And so what you need to compute is compute a flow. So what is a flow? So a flow is a non-negative vector that will denote as x, indexed by arcs. So this vector just says how much flow is going in every arc. That's what x means, and that's what we have to compute. So you have to compute the flow going over every edge, satisfying certain constraints. So the first constraint, maybe the obvious constraint, is the capacity constraint. So it just says that for all arcs E, the flow, so the flow has to be is non-negative, it has to be at most the capacity. It says you can only send the capacity, and this is the capacity constraint. And the other constraint is what's called flow conservation, which simply means that flow in is equal to flow out. Okay, so it just says that the flow that is coming into a vertex is the same as the flow that is going out of a vertex. Alright, so what we can say is, I will draw a picture here, and that will make the most sense. So if you have some vertex that I'll call V, and so you can look at all the flow that is coming in here, and you can look at all the flow that is going out, and whatever flow is coming in has to be equal to the flow that is going out. And the way that we can write this is simply say that again for all vertices V, so we can sum over all the flow that is coming into a vertex, so that would be all the in neighbors. So I'll use this for in neighborhood. In neighborhood is equal to the flow that is leaving, and I'll just call it W. This is the out neighborhood. Okay, so this is flow conservation. So these are the constraints. And what we want to do is we want to maximize the flow. And so we want to maximize the total flow that is going out of S. Okay, so sorry, I should have said something. For all vertices V, not equal to S or T. So S is a source and a sink. And the sources and sinks don't have flow conservation, because the source is sending flow and the sink is getting flow. And what you want to do is you want to maximize the total flow that is going out of the vertex. So we want to maximize this quantity. So we'll say for all, I'm using U, so I'll just use U again. For all vertices in the out neighborhood of S, we're looking at SU. We want to maximize this flow. Okay? And a simple exercise is that the total flow that is going out of S is the same as the total flow that is going in to T. Right? And this is basically just flow conservation over all the other vertices. So think of it as if you're sending trucks out of S, and trucks are not allowed to stop anywhere, that's flow conservation. Well, the trucks have to end up at T. And how many trucks end up at T? Exactly the number of trucks that you sent from S. Okay, so any questions about that? Any questions?
My questions, it's a bit abstract. Maybe you'll dive in more with an example, but like the idea of sending flow, like, are you trying to track the maximum size of all arcs on your path, like the largest capacity or the smallest? Well,
no, capacities are constraints. You are trying to send the maximum amount of flow. So think of it this way, right? This is, the example given is often you have a company, and S is a factory and T is a warehouse. So you have to send all the goods from the factory to the warehouse. But you cannot send all of it along one path, because maybe a road has a capacity. You can't send like 50 trucks on one road. And you have all of these trucks. So for every edge you say, well, this is the maximum number of trucks I can send along this edge. How many trucks can I send all together? Now what each truck is going to do is it's going to go and it's going to eventually go along an S and end up at T. Right? So every truck is going to take some amount of goods, start at S and end up at T. What is the maximum number of trucks that you can send when you have capacity constraints on all the edges? So for example, if your graph had some kind of a bottleneck, like let's say over here, the capacity here was 5 and 5. Then no matter what you did in this side, you can only send 10 units of flow. And so what we want to do is we want to compute what that maximum flow is going to be. Does that make sense?
Yeah, that helped. And I was confused if there's a temporal.
There is no temporal. There is no time here. And if you're confused, just look at these equations. These are a bunch of equations, and you need to maximize this. You need to maximize the sum subject to a capacity constraint or a flow conservation constraint. Okay?
Just one little note. Did you mean T at the bottom right? The in neighborhood of T?
The in neighborhood of T, thank you very much. Yes, you're right. It's the in neighborhood of T. Thank you. And by the way, you can prove this by basically summing all the flow conservation constraints at all the other vertices. And you'll see that everything else cancels out, except for these terms. Another small exercise is to show that, without loss of generality, for all vertices UV, either XUV or XVU is 0. And I say without loss of generality, meaning that in a maximum solution, you can assume that one of these is going to be 0. Because you're trying to send from S to T. There's no point in sending some stuff from here and then sending some stuff back. Like if you're doing, you could just remove all of that from the system. Does that make sense? So you're sending trucks, if you're sending 5 trucks from here to here, and then you're sending 5 trucks back, there's really not much point. You can just get rid of all of those, that part of the flow. It is not temporal, right? So you shouldn't think of it as temporal, you're just thinking of it in terms of these equations, but often this is used in temporal situations. And we can talk, you can actually then think about time, and you can say, what if you wanted to minimize the time that they're going to take? And there's a notion of min-cost flows, and there are various more complex versions of maximum flow. But this is like the fundamental problem. This is an extremely important practical problem. There are so many other problems that can be cast as flow problems. And indeed, a lot of people who worked on flow problems in, I'd say about the 70s and 80s, eventually some of them did build companies which were doing operations, what was called operations research, for large, let's say, like factories, whenever goods are transferred, airplane movement. A lot of these questions often are related to flow problems, where you have goods and you're trying to send them from one place to another, and you have capacities. Okay, so that is max flow, the basic description of max flow. Just so that I sort of can follow, raise your hand if you have seen max flow before, so that I can sort of gauge on how much to cover. So, okay, a few of you, okay, so maybe about half of you have seen max flow. Okay, so how does one solve max flow? And this is the first algorithm was given by Ford and Fulkerson. And again, the way to think about these, just as we thought about it in matchings, is to say, suppose you had a matching and you wanted to increase the size. It would say, suppose you had a flow and you wanted to send more flow. So consider any feasible flow. What does feasible mean? Feasible means it satisfies the constraints. Can someone give an example of a feasible flow? What would be the easiest feasible flow?
Everything's 0?
Everything is 0. That's a feasible flow, right? Because it satisfies the capacity constraint, it satisfies flow conservation constraint. So there exists a feasible flow. Now, suppose you have some flow. What we'll do is we will compute something called the residual network. Which I will call G sub x. And I might remove the vector notation just because it ends up becoming clunky when I write. So G sub x. So what G sub x will do is to basically change the capacities of the graph accordingly. So we will reset capacities. So we'll say the capacity of UV is going to become C UV minus X UV. So let's just assume that some X UV is strictly greater than 0. Right? So there is some edge in this which is sending some flow. So suppose the capacity of this, let's say the capacity was 100. And if you're already sending 10 units of flow, it means that the residual capacity of this is 90 units. That's this. It's just saying that you reduce the capacity of that edge because you're already sending 10 units of flow. Right? So in your residual network, you will set the capacity to be 90. Now here's the interesting part. It says, well, okay, you could say, well, I'm just going to do this and then see if I can route more flow. And it's like, well, no, maybe the right thing to do is to reduce the amount of flow on this edge and send it some other way. How do you allow the algorithm to reduce flow if this is what you do? So Ford-Fulkerson does something very clever. It's going to put a back edge. It's going to put a back edge and increase the capacity over here. So let's say you're in a situation where the capacity here for this edge over here was 100 and the back edge had 0 capacity. So you're not allowed to send flow backwards. Because we've already put 10 units of flow, we are actually going to allow a capacity here to be 10. So what we do specifically is we do C prime of VU is whatever the original capacity was plus XUV. Right? XUV is the same, but here it's VU. So you put a reverse edge and you increase the capacity in the reverse edge because it's almost like saying you get to cancel out that flow by sending it in the opposite direction. Okay? Does this make sense? So this is the residual network. What you do is you simply take your graph and you make these changes. You simply update the capacities and you get you have a new set of capacities. Note that because this is feasible, the capacities are still non-negative. They are still non-negative. Okay, the capacities are still non-negative. Can someone give a reason why? Why is it still going to be non-negative?
Because XUV has to be less than the capacity?
Exactly, because it's a feasible flow. You started with a flow that was valid, it was feasible, so XUV has to be less than the capacity. So when you reduce it, you're going to have something negative. And in the second part, we're adding. So the capacity is only going up in the reverse direction. Does this make sense? Any questions about the residual network?
I had a question. I think I'm kind of confused. Since are we choosing one of the edges, like one direction of the edge for all of them? Is that how we're starting it off?
Yeah, well, okay. I said that without loss of generality, for every pair, one of them is 0.
Mm-hmm.
So you only have to reduce with the one that is non-zero. You can.
How do we know which one is non-zero?
No, you start with a flow. So you pick a flow.
Uh-huh.
And you pick so it's like saying that you have at this point come up with some partial solution. In that partial solution, for every UV, either XUV or XVU is 0. So only one of them is non-zero.
Oh, I see. Okay.
And then you construct the residual network from that solution.
Okay. Thank you.
Okay? Things... Does that make sense? Any questions?
So the last one is the reverse arc
Mm-hmm.
doesn't have to be 0 in this example, right? It could have been also 50
Yeah.
or something.
Yeah.
It
So
would have had 60 or whatever.
exactly.
Right?
So
Plus
then,
10.
if the reverse was 50, then C prime would have been 60. Exactly. Because it's kind of saying you get to cancel out the 10 units of flow and then send 50 units more flow. Does that make sense? Right? You get to cancel out whatever flow is currently being sent. And then on top of it, whatever capacity is there in the reverse direction. Right? Questions?
So one more, I can't remember, the flow conservation,
Mm-hmm.
it reducing from one arc but increasing on the other doesn't seem like it keeps the flow conservation, right? Like, shouldn't you increase both or decrease both by the same amount?
You are not doing flow conservation on the capacities. Flow conservation is on the flow vector. I'm changing the capacities. The capacities don't satisfy any any conservation constraint. Think of it as actually you were sending trucks, right? And you're allowed to send at most 100 trucks in this direction. So currently you have a solution where you sent 10 trucks in that direction. You can update your solution by reducing the number of trucks in that direction. The amazing thing about the Ford-Fulkerson, the residual network, is it allows you to think of it as if you're sending more trucks in the reverse direction that cancel those things out. You are not conserving capacities. You don't need to conserve capacities.
Do the back edges exist already, or do we create them?
If they exist, you would add the capacity. If they didn't exist, you would create them. Right? You would just imagine that an edge that exists is one whose capacity is non-zero. Right? If the capacity is 0, then you could think that that arc does not exist. And so you would create arcs through this. Okay? We'll see a small example right now which might make some things clear. So I'm going to draw a very simple network. And actually we'll see that, this is actually a classic example as well. So suppose here are S and T. And I'm just going to draw these arcs. I'm going to put one arc over here. The capacity is here. I'm going to call them capital U. The capacity there is 1. So think of capital U as something really large. So it should be fairly obvious to you that the max flow is 2 times U, because you can send U units of flow on the top part, U units of flow on the bottom part, and this gives you a max flow of 2U. Right? Suppose you wanted to do it through a residual network. I mean, of course, that gives you a simple solution, but let me give you a solution that seems like it's more complicated, but it actually ends up being an obstruction. Suppose you decide to, instead of sending flow along this path, so let me give these vertices some names. I will refer to this as X, maybe not X, let me call it, I used X for flow, so let me refer to that as C. I'm going to refer to this as D. Okay. So instead of sending flow from S to C to D, you could send from S to C to D to D. You could imagine sending 1 unit of flow along that direction. Okay? Does that make sense? So how many units of flow can you send along that one path?
One?
1 unit of flow, right? So you could send 1 unit of flow. Right? So this gives you now you'll compute the residual. Now the residual is going to be S. Here you have a capacity of U minus 1. That capacity remains U. You'll put a back edge of 1, saying that, well, I could have also sent 1 in the opposite direction, although you'll never use it. And so here is U. That's going to be U minus 1. You're going to put 1 unit there. So you've eaten up the capacity on this, but you'll have an opposite capacity of 1. That's the residual, because you sent 1 unit here, and so you could cancel that out. And so in the next term, given this residual, you could send S to D to C to D. You could send 1 more unit that way. Now, if you think about what is the net effect of sending both of these, when you sort of add these things up, when you add them up, that's just sending 1 unit of flow from S to C to D and S to D to D. Because the CD flow and the DC flow are cancelling each other out, because they're going in opposite directions. So if you add them, they're cancelling each other out. But at each individual step, you can just think of it as, I have a flow problem and I'm going to route. And then when you compute the residual for this, what is going to happen is you're going to have U minus 1, 1, U minus 1, 1, U minus 1, 1, U minus 1, a reverse of 1, and now you have a forward flow of 1. Now you can repeat this. You can go back and do S to C to D to T, send 1 unit of flow, flip that edge, and then keep repeating. Now if you keep doing this, eventually in 2 times U iterations, each iteration sending 1 unit of flow, you will finally get a max flow of 2U. Clearly that was not the most efficient way of doing it, but that works. And that shows you the residual, right? So even though you're not allowed to send flow from D to C in the original network, in the residual, you are allowed to send that flow, because in effect you're cancelling out some flow from before. So it's, what you're doing is you're effectively like putting each flow path on top of each other. Each iteration you compute some flow and you kind of add things up, and you will cancel out flow that goes backwards and forwards along a particular arc. Does that make sense? Does this help? Any questions?
So we're not finding the actual path. I mean, it just seems to work out to the same max flow had we taken the optimal path. Yes. By calculating this residual. Like, yes. The jump from doing the back edge, how it figures out to still be the same as the optimal path, I think, like, yeah, how do I make that leap?
So the way to think about it is, in some sense, okay, so formally speaking, it's induction. You prove it by induction. But maybe the way to think about it is, there is a notion of flow cancelling out. Because of this exercise, when you have flow that is going from U to V and V to U, you can kind of remove that. Does that make sense? You can almost think of it as like, I think the problem with particles in the system is that, they always add up. They don't cancel each other out. But with flow, you think of it as flow going from U to V, and flow going from V to U can cancel each other out. Does that make sense? So when you have, ignore the direction for a second. Ignore the fact that there are arcs. Let's just say that in every edge, the capacity in going forwards and backwards is the same. It doesn't matter. So suppose you decide to send 5 units of flow in the forward direction, and you had another path that was sending 5 units of flow in the backward direction. When you add these paths together, then in effect they send no flow in that one edge. And that is sort of what is happening over here. When you add up this flow, the flow that goes from S to C to D to T, and S to D to C to T, the flow going along C and D will cancel out. ignore the fact that there are arcs. Let's just say that in every edge, the capacity in going forwards and backwards is the same. It doesn't matter. So suppose you decide to send 5 units of flow in the forward direction, and you had another path that was sending 5 units of flow in the backward direction. When you add these paths together, then in effect they send no flow in that one edge. And that is sort of what is happening over here. When you add up this flow, the flow that goes from S to C to D to T, and S to D to C to T, the flow going along C and D will cancel out. you have to be careful, like everything here is non-negative, and that is deliberate, that we only think of non-negative flow. And I don't want to put negative numbers because then that starts confusing, but in effect the way that that is being done is by resetting the capacities. So you sort of add this capacity in the backward direction.
I see. That's what you meant by overlaying them. Okay, that made a lot of sense.
Yeah.
Thank you.
Okay, any questions? Alright, so this algorithm which I just described is the Ford-Fulkerson algorithm. So what does the Ford-Fulkerson algorithm do? Ford-Fulkerson algorithm will say that, so the first step is, you just set the flow to be all zero. This is a feasible flow. And you'll say while there is an S to T path in the residual. While there is a path in the residual, so take that path, any path. Right, so you've computed some residual, and now there exists some directed path. And this has a word, this is called the augmenting path. And then send as much flow as possible along this path. So this is going to update the flow x, update x, and you recompute g of x. This is the Ford-Fulkerson algorithm, and it's, I think, maybe in the 50s or 60s. And you can see that every time it keeps adding more and more and more flow. It keeps adding more flow, and one can argue, essentially you can apply induction, and you can prove that the Ford-Fulkerson algorithm will eventually converge to the max flow when the capacities are integral. I know it tends to be a little tricky when the capacities are are irrational numbers, then weird things happen, but that often never happens in practice. So when the capacities are integral, every time you augment, you send at least 1 unit of flow. Right? So this is going to be at least 1 unit of flow. And that's because capacities are integral. And how do you find a path? Well, this is just, you can do BFS, DFS, you can pick any algorithm you want. And so you have the fundamental theorem of Ford-Fulkerson that says that the running time of, the fundamental theorem is that Ford-Fulkerson computes the max flow. And the running time of Ford-Fulkerson is O of m times u, where u is the max flow. Right? So the running time could actually depend on the output, which is really bad. So this is an exponential time algorithm. This runs an exponential time. Right? Because the representation of u is log u. So this is an exponential time algorithm. And indeed, when can this happen? I just showed you an example where that's going to happen. If Ford-Fulkerson were to pick these paths, which it could, right? It just said pick some path. And while over here, it looks like, oh, the obvious thing is to go from S to C to T. But this is obvious because I've drawn it that way. Suppose what you had here was some complicated graph. Suppose it wasn't an edge, it was some complicated graph which could send you units of flow. So maybe there's some really complicated network over here. So it's plausible that your algorithm that does DFS to find the path is going to take that one edge. Or maybe the one that does BFS is going to take that little edge. And once it takes that little edge, and that little edge is going to flip, and then this could keep happening. Nonetheless, it still converges. So this is Ford-Fulkerson. Any questions about Ford-Fulkerson? Right? This is an exponential time algorithm. And what I want to discuss is the Edmunds-Karp algorithm. Or it's not really an algorithm, but rather a deep insight that simply says choose augmentations along shortest paths. And shortest is just the number of arcs, right? Just vanilla shortest paths. We're not looking at the capacities. It just says look at the shortest path according to the graph structure. Choose augmentations, shortest path. Then the Ford-Fulkerson algorithm converges in polynomial time. It's remarkable, if you actually choose the shortest path and you start using the capacities, you can actually, this won't happen, but you just choose augmentations along the shortest path with arcs and it converges in polynomial time. That's the Edmonds-Karp result. And I'm going to prove the Edmonds-Karp result to you. And we'll see that there are some key ideas here that are going to come back to be useful for bipartite matching. Any questions? Yes.
Do they only ever care about the max flow more than the actual path for the flow itself, or?
Well, I mean, once you get the flow, you actually can reconstruct the paths from it. And if you think about the flow, it's not just the value, what you get is the flow. So it tells you how many things to send along every arc. Does that make sense? Like you can recover all the paths from the flow. I mean, this you can ask me later, but once you have the flow vector, then essentially you can do lots of things with it. Okay. Just a quick poll so that I see. How many of you have seen Edmonds-Karp before? Raise your hand. Okay, so only 2 of you, that is good. So there's something, this is new. Alright, so let us actually prove the Edmonds-Karp, and it's a very clever argument. So let X be a flow. So let X be a flow. And X prime be the flow after a single augmentation along the shortest path. The shortest path in G of X. So remember that we had, so I'm just going to disable the bells, some more line. Okay, right. Okay. So this definition makes sense. So X is a flow, you perform a single augmentation along the shortest path and you get X prime. Now I'm going to define dx to be shortest path distances in G of X. And similarly I can define d of X prime, which is the shortest path distance, the same thing, in G of X prime. So here's our first claim. Our first claim is that for all vertices, d of x prime of s to v, so you start from the source, you go to v, is greater than or equal to d of x from s to v, and d of x prime from v to d is greater than d of x from v to d. What this is saying is that after doing an augmentation, the shortest path distances never decrease. They never decrease. They're always, they either stay the same or they go up. Okay, so let's give a proof of this statement. So let's prove by contradiction. Suppose there exists a v such that d of x prime of sv is strictly smaller than d of x sv. Okay, so there's some vertex. So you did an augmentation and the shortest path actually reduced. Let v be chosen to have smallest, we'll say smallest dxsv value. Meaning that you just pick the vertex that has the smallest such value. So this is, you're saying suppose there exists a vertex that violates this claim. And pick the vertex that actually has the smallest distance that violates the claim. Okay, so let's just draw a picture. So this is S, here is V. Okay, and what I'm going to do is I'm going to take a shortest path. This is the shortest path in Gx prime, in the residual network. So I'm just taking the shortest path in the residual network, in after doing, the augmentation. So before the augmentation we had a picture, we did the augmentation, that gives the flow x prime, and we're looking at the shortest path to v. And so it goes through some vertex w. Right, and w may actually just be s. It's also possible. Okay, so I'm going to write a bunch of things down. So dxsv is strictly greater than dx prime sv. This is by assumption. This is what we assume. Now what is the distance in x prime from s to v? This is the distance in x prime from s to w plus 1. Okay. And now I'm going to argue that this is greater than or equal to dx SW plus 1. Why? The first one is assumption. This is what I assumed. This is because it's the shortest path. Why do I get the third inequality? Any thoughts? V was a counterexample with the smallest dxsv value, which means W, shortest path, was actually smaller. Does it make sense? Now this is the smallest counterexample. Smallest counterexample. Maybe I should be. My apologies, right? So I chose it to have the smallest dx prime value. So w has a smaller distance in gx prime, and therefore w is not a counterexample. Right? This is sort of the minimality. This is the minimality of x. Minimality of, of v as counterexample. So the net, when I just write it out together, I get dxsv is strictly greater than dxsw plus 1. So this says that the shortest path distance in x, in g of x, from s to v is strictly greater than that of s to w plus 1. This implies, hence, wv is not an arc in g of x. Right? Because if it was an arc in g of x, then this would be a shortest path. Then this would be a shortest path in g of x, implying that dx of sv is equal to ds of sw plus 1. Just write this as an exercise to sort of state it more formally. So wv is not an edge in gx, but it is an edge in gx prime. So how could you get such an edge in gx prime? I should say arc. How can you get this arc in gx prime when you didn't have it in g of x? How did this arc appear? How does an arc appear? Yes? Any thoughts?
Is it when you update the flow, you create a new backwards maximum capacity, creating a new path?
So look at this example, right? Here's an arc DC that appeared even though it wasn't there before. Right? This arc appeared. DC appears even though it wasn't there before. Why did DC appear? It appeared because you sent flow along CD. Does that make sense? When you send flow in one direction, you put an arc in the opposite direction, right? You add capacity in the opposite direction. So what this is saying is that WV was not in G of x. So WV had no capacity in G of x. But in G of x prime, it ended up with capacity. So you added this backward arc. So specifically now tell me, you're right, it came up. Can you say something about how flow was routed in G of x? This edge appeared from in G of x prime. So what happened in the augmentation within G of x that made this edge appear? Where was
flow
flow
routed from V to W?
There was flow going from V to W. Exactly. So this means the augmenting path found in G of x used the arc VW. Okay. So this arc was present in G of x, which was the shortest path. So what did G of x do? G of x used arc WV. So G of x, the augmenting path, so let me call this path P. P goes from S to V, and then uses the edge VW and then goes to D. Right? That's what it did. It went to V to W and then to D. And this was the shortest path. This was the shortest path. Okay, now for the magic trick. So that means the dx from S to W is equal to dx S to V plus 1. Right? Because this is the shortest path. And the shortest path went from S to V to W and then went somewhere else. Went to D. So you know the dx SW is equal to dx SV plus 1. Okay, now do you see the contradiction? Now do you see the contradiction? Right, so where's the contradiction now? dxsv was strictly greater than dxsw plus 1, but here we deduce that dxsw is equal to d of sv plus 1. So this is a contradiction. There's the contradiction. And that completes the proof. That completes the proof for the first statement. The second statement is analogous. It's basically the same argument. Right? Questions? Questions?
This is a silly one. I just don't understand. What does it mean to say to have smallest dx prime value?
So
I thought D is already the smallest, is the shortest path.
okay, so this was badly phrased on my part. My apologies. So suppose there exists a vertex which is a counterexample. Right? Let V be a counterexample chosen to have the smallest dx prime sv value. So there are many possible vertices that have this property, meaning that they're violating your claim. And I am choosing the one that is closest to S that violates the claim. Does that make sense?
Yeah, thanks.
You don't seem convinced, so maybe you should ask a follow-up.
I'm still parsing the contradiction.
Okay, so my point is this, right? So it's a proof by contradiction. So what it says is, here is some condition you've stated. In a proof by contradiction, we're saying, well, there must be a vertex that doesn't satisfy this condition. Right? So here's your graph. Here's S and T. And so there are many vertices that don't satisfy this condition. I'm going to pick the one that's closest. And I'm going to call that V. Now, why is this convenient? Because I know that anything closer does satisfy the condition. And I'm going to use that fact in my proof. Does that clarify a bit? It's like you're picking the vertex that's closest to S to get the proof to go through. Okay. So now that we have this statement, and if you miss the proof, you can go back and look at it. Don't worry about the proof specifically. I mean, the proof is important, but we can step back and say, okay, what we know is that when you do the Edmonds-Karp augmentation, the shortest path distances keep going up. So the augmentations happen in stages. In each stage, dxst is fixed. So there are at most n-1 stages. Because the shortest path, distance from S to T, So the point is the shortest path distance from S to T can never decrease as you're doing these augmentations. So let us break up all the augmentations into stages where within a stage the shortest path distance from S to T is fixed. There are n-1 such stages, right? In each stage the distance is fixed and the distance can only go up to n-1. So it starts from potentially from 1 and goes up to n-1. Or at most, I guess maybe I should say technically there are there are n-1 stages. There are n-1 stages. What happens within a stage? And so the claim, well, okay, so before I get to that claim, let's talk about what happens in a stage. So consider an augmentation. Consider augmentation along a path, I'll say I'll just call it V0, V1, V2, up to Vi, which I'm going to call T. So there's some augmentation from S to T, and there's some augmentation. How much flow do we send? The flow sent, so essentially what we can do is we can find the minimum capacity along everything that's over here and send that much flow. We'll send, the flow sent is the min, I'll say over all j, or j going from 0 to I-1. So you look at all the edges here and you'll send the minimum, so C prime of Vi plus 1. By prime I mean the capacity is at that stage, right? This is the capacity in g of x, in the graph at that point. So the flow sent is the minimum capacity along that edge. So therefore, after sending this flow, one of these capacities becomes 0. Why? Why does one of the capacities become 0 after sending this flow?
Because we've sent the min of one of them. The min of all of them is the value of one of them.
Exactly. The min is one of them. So there's going to be some edge over here. So maybe it's this edge. So let me just draw out this picture better. So maybe this edge is the min. And so we're going to reduce its capacity. And so we're going to basically get rid of that edge and put a back edge. We're going to put back edges everywhere. But we will remove the capacity of that edge. So one of these capacities becomes 0. This arc is saturated. That's what we mean by saturated. Saturated means its capacity becomes 0. Capacity becomes 0 and the arc is removed. It might come back. Right? It might come back if in a later stage we send flow in the opposite direction, the arc is going to come back. And that example, if you recall, was this first example I did, where the arc would disappear and it would come back and it would disappear and come back. Right? So just because an arc disappears doesn't mean it cannot come back. But what we do know is every time we send flow, one arc disappears. But we're going to create some new arcs. So here is sort of the deep observation is within a stage. So what is a stage? In a stage D, the distance from S and T is fixed. Within a stage, an arc can be saturated at most once. Which means that every arc can get saturated at most once. It may reappear, but it's never going to get saturated again. what does that tell you about how many augmentations can happen within a stage? How many augmentations can happen in a stage then? Just by this claim, how many augmentations happen? Yes?
Would it be the number of different paths from the start to the end?
But that could, okay, so that would be one guess, but that's an exponential number. You can do better. So an arc can be saturated at most once in a stage, right? And in a stage, it's when DST is fixed. The shortest path distance is the same. So the way to think about a stage is the shortest path distance as you do the augmentations is continuously going up. It's either staying flat, it's staying the same or going up. It's monotonically non-decreasing. Within a stage, an arc can be saturated at most once. How many arcs do you have? How many arcs are there in the graph? Yes, how many arcs can there be in the graph? Someone?
N-1 would be the cap.
No. How many edges are there in the graph? That's just an arc is a directed edge. How many edges are there in the graph? O of m. M, right? M is the number of arcs that are there. O of m. And every arc is going to get saturated at most once. So in a stage, there are only m augmentations. And there are only n stages. So the total number of augmentations becomes m times n. Whereas previously we had no bound. Within a stage, an arc can be saturated at most once. Right? So within a stage, you can never go through this, you will never saturate the same arc twice, which means the total number of augmentations is O of m. Okay? So what is the proof? So consider an arc UV that gets saturated. So let's draw the picture here. So from S to T, there's some path, directed path.
Sorry, were we using the word augmentation in this case just to find a path?
So
augmentation
augmentation is just any, like when you look at Ford-Fulkerson, right, you compute the residual graph, you find any path from S to T, and then you send all the flow in that path. Right? So you can think of this as the augmentation. Does that make sense? Like this is when you send flow, right? You pick a path and then you send flow. And we're picking shortest paths in G of x. Okay, so consider some edge arc that gets saturated. Now what do we know? We know that the shortest path distance from, and let's just say the flow at this stage, is x, right? So dxst is dxsu plus 1 plus dxvt. Right, so we'll say x is the flow before the augmentation. Right, and then we're going to compute this path. We're going to send flow over here. Okay. So at any subsequent x prime, we know that dx prime of SU is at least dx of SU, and dx prime of VT is at least dx prime of VT, and this is just the previous claim. And so we know that the distances are always increasing or non-decreasing. Now suppose some augmentation, some augmentation uses VU. Now, why am I saying that? So here's an edge that got saturated. This edge is going to disappear. The only way it reappears is if some augmentation use the opposite direction. Right? So what happens? So consider an arc that got saturated. So once it gets saturated, this back edge is going to form. The only way that VU can reappear, this is the only way that UV can reappear, is if some augmentation uses VU. So let's say some augmentation uses VU at some flow x prime. So x prime is some subsequent flow, and some augmentation decided to use VU. So there's some flow that goes from there to there, and then it goes from there to there. Now, if we look at the distances, we will end up with our contradiction. So what is the shortest path distance from S to T? Well, this is S to V, because it's going in the opposite direction. It's going to V to U to T plus 1 plus dx prime U to T. Now this, just by the monotonicity condition, is I can replace the x's, x primes by the x's. Now dxsv, this I can replace by dxsu plus 1. That's an exercise. It's basically because it's in x we used shortest paths. The path given here was the shortest path. Plus 1 plus, right, so this gets replaced to that. 1 goes over here. Plus, I can now write dx vt v comma t plus 1. Again, that's an exercise. Again, this is just shortest paths. So what I get is dx su plus 3 plus dx vt. But I know that dx of st is dx of su plus 1 plus dv of dt. So this means this is dx of st plus 2. That means it's a new stage. That means the next time flow actually goes in the backward direction is a new stage. So for the arc UV to reappear, it has to be a new stage. Therefore, within a stage, an arc can be saturated at most once. And now this sort of completes the argument. There are at most n-1 stages. Each stage has O of m augmentations, and each augmentation takes O of m time, and hence the theorem of Edmonds-Karp is that the max flow can be computed in, if you multiply all of these together, you get nm squared time. So you have polynomial time. So this is polynomial time. And my understanding is this is the first polynomial time algorithm. Again, it was given in the 70s. Since then, there have been multiple improvements. But it's remarkable that such a simple change to Ford-Fulkerson, which is just using shortest path, allows for a polynomial time algorithm. Now, what I'd like to talk about in the remaining, which is not much time, in 10 minutes, just to tell you a little bit about Hopcroft Carp. And this is the improved algorithm, improved bipartite matching. So here is the first question that was addressed by Hopcroft Carp. Is it, suppose you did bipartite matching, and recall that you can convert bipartite matching to a max flow problem, right, which is the Ford-Fulkerson algorithm that we discussed in the first lecture. How many stages exist? So interestingly, we'll show that for, remember we said there are at most n-1 stages, at most basically n stages. For bipartite matching, we can improve that bound significantly. And so here's how I'm going to do it. So suppose the max matching m prime has size k, and let's say the current matching has size at most k minus root n. What we'll show is that when the matching is significantly smaller, there actually cannot be too many stages. And the moment that matching becomes sufficiently large, there aren't going to be too many stages left. So that is the argument. Okay, the current matching M has size at most k minus root n. So remember we talked about the symmetric difference M transpose M prime, which is a disjoint collection of alternating paths and cycles. Each such path with more m prime edges than m edges is an m augmenting path. Right, so remember that you had this, if you had an alternating path, so I'm going to make these as m prime. I'm going to do the squiggle for m. If you have any path of this form, this is an augmenting path because you could do the flip and you can increase the size of m. So each path with more m prime edges than m edges is an augmenting path. And if it's an augmenting path, then we know that we can increase the size of the matching. How many more m prime edges are there than m edges in any such path? How many more m prime edges are there? Yes? How many more?
Is it root of n in your example?
In a single path. In a single such path, how many more m prime edges are there than m edges?
Just one?
Just one. Just one. So what you have is a collection of cycles and alternating paths which may also do the opposite. Right, so these are the three types of alternating paths and cycles we have. We have one of them where there's one more M prime edge than an M edge. We have the cycles where the number of M and M prime edges are equal. And then we have the other kind where the number of M prime edges is one less than the M edges. Alright, so now here's what we're going to argue. This is at least root n. The difference between this is at least root n. Now I claim that this is at most the number of M augmenting paths. Which are disjoint. Right? The difference, because we know that M prime minus M is at least root n. That's what we assumed. So there have to be many augmenting paths, because it's only in an augmenting path that you have more M prime edges than M edges, and you have at most one. This is an exercise, and I'm probably going to force you to do it. So please ask me questions if this is not clear. Sure, I should say vertex disjoint. Does this make sense? If M prime minus M is at least root n, or whatever it is, then there have to be at least root n M augmenting paths, just by looking at the symmetric difference. And all of these are vertex disjoint. Hence, there exists an augmenting path of length at most n divided by root n, which is root n. It says that if there are root n augmenting paths, and all of them are vertex disjoint, then there has to be a path whose length is small. Right? This is an averaging argument. So this is another exercise. And this is basically just averaging. It's an averaging argument. So this is the key. It says that as long as the current matching has size at most root n, is at most root n less, the current matching is k minus root n. So it's root n less than the max matching. Then there is always an augmenting path of length at most root n. Which means the augmenting paths are all going to be short. They're all going to happen in these first root n stages. And that gives me the claim that after root n stages, that means when augmenting path has length at least root n, the matching size is at least k minus root n. It means after root n stages, we're very close to the maximum. We're at most root n away from the maximum. So after root n stages. Okay, so now what happens when the maximum size is k minus root n? How many more augmentations can be performed? How many more augmentations can be performed after the matching size is k minus root n? So the question is so in each augmentation, so think of the Ford-Fulkerson for bipartite matching. Every time you augment, what happens to the matching size?
Increases by 1?
It increases by 1, exactly. Good. It increases by 1. Now let's say the matching size at some point is k minus root n, where the max matching is of size k. How many more augmentations are you going to perform?
Root n?
At most root n. So we have root n stages where the augmenting path is short, and then after that we're only going to perform root n more augmentations. So it turns out, another way of saying this is there are at most root n stages. At this point the augmenting path has length at most root n. After this, there are at most root n augmentations. Let alone stages, there are at most root n augmentations. So the total number of stages is actually O of root n. It's at most root n. So there are only root n stages when you do bipartite matching. Now this doesn't really give an algorithm yet, because the question is how to implement a stage efficiently. And we've run out of so how long do we go till? Do we go to 8:45 or 8:40 or what is it? I always lose track of time. Are people awake? Should I proceed a little further for another like 5-10 minutes? Raise your hand if you can.
It ends at 45.
8:45. Okay, all right. So why don't I continue? Let me sort of finish what I'm going to say, and then I might convert some of this discussion into exercises. I'll sort of give you the punchline. It turns out that we can implement an entire stage in O of m time. This is only for bipartite matching. So there are root n stages. Each stage runs in O of m, and so Hopcroft-Karp, the Hopcroft-Karp algorithm, which I may be missing the exact time. I think it's in the 70s. It's very close to Edmonds-Karp. Is bipartite matching. Can be done in O of m root n time, or I should say bipartite max matching, right? And it took almost a quarter of a century to beat this bound. So this was only beaten a few years ago for sparse graphs. Getting an improvement was a significant effort. Like, this is a very basic algorithm that one can teach in a course. The improved algorithms requires a lot of numerical analysis and a lot of complex algorithmic techniques. So it was quite remarkable when the improvement came. But just to show you that it's very hard to beat this algorithm. So how does one implement the stage efficiently? We'll kind of draw some pictures for you to show you what's going on. Remember, how does bipartite matching work? So what we did is we directed all the matching edges backwards, and then we had this unmatched part. This was the part so all of this was matched, and then we directed all the other edges forward. So let me just refer to this as UL and UR. This is the unmatched part on the left, the unmatched part on the right, and we find a path from UL to UR, and that was the augmenting path. So the idea of Hopcroft-Karp is to find many vertex disjoint augmenting paths and augment simultaneously. So it sort of augments everything in one go. And the way it works is it basically, you sort of, using BFS, you can kind of build this sort of a graph. You build some sort of a layered graph which essentially contains all the shortest paths. So you can create a graph with all the shortest paths. So this is what it's going to look like. It's going to have a bunch of edges here. Then it has the matching edges. It's got a bunch of edges here. Then it has a matching edges. And then it's got a bunch of edges here. Something like this. So maybe the shortest path was 5. And it's going to find many paths in this graph, find all of them and augment all of them simultaneously. It requires a fair bit of proof to show that it actually works. But it basically uses the same ideas as Edmonds-Karp. This notion of distance and this, these sorts of pictures that you saw before of these sorts of arguments. When does an edge appear? When does it disappear and reappear? Using some of those arguments, you can show that a stage can be implemented in O of n time. That once you find all these vertex disjoint paths, the shortest path distance will actually increase in the residual graph. So I will end here and I will take any questions that you have. With this, I'm going to sort of wrap up at least a basic discussion of matchings and flows. And next lecture onwards, I want to talk about linear programming and trying to understand these algorithms from a more fundamental viewpoint of a continuous viewpoint with using linear programming.